Hello guys, this is CodeNCode and this is video editorial for the problem Kavi and pairing duty taken from Codeforces div 2 round 722D. And this problem was rated 1700 and we are going to solve this problem using dynamic programming. So let's go ahead and see what the problem statement is. So the problem statement is you are given two endpoints on the x-axis and you need to find the number of valid pairings, right? How we define valid pairings? See, there are two rules. These two must be valid, okay, must be followed. First rule is that one of them must, if there are two pairings A and B, then one of them must lie completely inside the other, or they must have the same length. It may seem confusing, so let's go ahead and understand with an example. And here you see there are three examples. So A is a valid pairing, B is a valid pairing, C is not. For example, in A we only have two pairs, these two, right? And one pair is lying completely inside the other. In B we have again two pairs, blue and red, both have the same length, so these two are good. Okay, now here we have three pairs, blue red, blue green, red green. Red green is okay because both of them have the same size. Blue green is okay because green is completely inside the blue one, but red blue is not okay. Why? Because see, neither both of them are having the same size, nor one of them is inside the other. Okay, so that's why since because of this pair, this whole setup, this whole configuration is actually invalid. So if n is equals to 3, that means we have 6 points, and you are going with this configuration, this is invalid one. Okay, so now you understand what is the problem statement. Let's see how many, for a given n, how many valid pairings exist, how many valid configuration exist of 2n points for a given n. Okay, let's go ahead and see that. So let's go ahead and see some of the observation. One of the first observation that you can make is that if you are pairing the first point, that is the first point, with point at position x, then all of the other points which are in the range x plus 1 to 2n should have the same size, same segment length as of the first one. Okay, what do I mean by that? Let's explain with an example. See here, the first point is being paired with the point at x position, right? So these two are paired. Now all of the points from x plus 1 to 2n, these 2 points should be having the same segment length as of this, the first. Why? See, these points are not completely inside this, so clearly they must have the segment with the equal length of this. So this is the first observation, right? So now before we move on, whether you are looking for DSA or system design or full stack development, or you have just started your programming journey, you can get access to courses and free classes for all these topics at Unacademy. Here you also have free access to live classes every day where many topics are covered which are very important for interview preparation for software development roles in top product-based companies. As a subscriber, you get access to all the courses and badges taken up by best-in-class educators from top product-based companies or among the best competitive programmers in the country. Dedicated doubt-solving sessions after every 3 classes in a course, and also a separate doubt support on Discourse where teaching assistant and educators will help you in clearing doubts. Most importantly, a structured learning path with a course plan designed specifically to help you upskilling and cracking interviews. So guys, relevant batches details can be found in the description and also linked to the free classes. You can also use my code and access all the free resources and get 10% discounts for subscription. So let's get back to our lecture. So let's see how we'll solve this problem. First of all, let's assume that dp of I, we will use of course dp, so we have a dp array. Dp of I will be number of valid pairings of 2i points. Okay, and also the solution would be dp of n, right? Because we have 2n points, so dp of n would tell you how many number of valid pairings are there. Okay, so dp of n will be the solution. Now observation 2 is says that if we have divided this whole pairing in two different parts, when one is paired with x where x is greater than n, and also in the other part where one is paired with x where x is less than equals to n. So what happens if one is paired with x where x is greater than n? Okay, now here you see, suppose this is an example, one is paired with 6, n is 4, so one is currently paired with x where x is greater than n, clearly, right? So here you see how many pairs are left. Pairs left are x minus n minus 1. Okay, x is 6, 6 minus 4 minus 1 is clearly 1, so one pair is left to be taken care of. Okay, if one is paired with x plus, x. If one is paired with x, then the other point needs to be paired with x plus 1, then other point needs to be paired with x plus 2, and so on till we reach 2n, right? So here we when at position 3 we are able to reach 2n, this will be paired with 2n, so we will stop here. How many pairs are left? Why we are doing this? Because all of this must have equal length, right, from observation 1. So that's why we are pairing like this, so that all of them have equal length. After that we are left with these these pairs. Now when we are left with these pairs, now we all again have the same responsibility to find out how many ways we can actually find out configuration to pair these many left points, right? And this is exactly the same problem that we are actually solving, but with a smaller input, right? Initially we have to find the answer of find the total number of valid pairing for 8 points, right? Now we are left with only 2 points, but the problem is still the same. We have reduced the input, but problem is still the same. It will be better to understand with bigger example. So suppose if I paired 1 with 7, then 2 will be paired with 8, and now we'll stop. How many pairs are left? 7 minus 4 minus 1. Of course there are 2 pairs left, right? Now since there are 2 pairs left, we need to find the number of pairing of this. Again, this is the same problem as the original one, but with the less input, right? Smaller input. And this is one of the property of dynamic programming. This is optimal substructure property, right? Because to find the solution, you can utilize the solution of smaller sub problems to build the solution of the actual problem, and that is exactly what we are doing here. Now we are left with a smaller input, and now we have to find the solution of this. But if you see, we will incrementally find out solution. So when we are finding dp of 4, we have already calculated dp of 2, because now for this it's actually how many ways you can pair these 2n points, right, where n is this time 2, which is valid, which will be your dp of 2, right? dp of 2 tells you number of valid pairings of 4 points, and that is exactly what we want here. How many ways we can pair them? dp of 2. So that's why dp of 2 will be added to dp of n. N is currently 4 here. We are calculating for dp of 4. Okay, so dp of 2 will be added to the solution of dp of 4. Why? Because if there are x number of different ways you can pair 4 points, take these two as it is, and each time replace the configuration, 4 different configuration, then you will have 4 different pairings, right, with 8 points. And that's why dp of 2 will be added to the solution of dp of 4. Is it the only thing? The answer is no. Actually, x can range from n plus 1 to 2n, because we are taking x which is greater than n. So x can be from n plus 1 to 2n. So this number of pairs will vary from 0 to n minus 1, right? So dp of n will actually be sum of dp of 0 plus dp of 1. When it is dp of 0, there are no pairs left. dp of 1, only 1 pairs left, and so on and so forth. When 1 is paired directly with 8th point, that is 2nth point, then there are exactly n minus 1 points left. And that's why dp of n is equals to sum of, prefix sum you can say, of dp array from 0 to n minus 1, right? But if you see, we haven't taken care of this second condition where 1 is paired with x where x is less than equals to n. We have seen what happens when 1 is paired with x where x is greater than n, but now we are taking care of the condition where x is less than equals to n. What happens is that we have already seen that in observation 1, that in this case all of the segments should have equal height, right? Equal height, I'm saying, sorry, equal segment length, and hence their length should be divisor of n. This is hard to understand without an example, so let me give you an example. Here it is. See, this is n is equals to 6, so we have 12 points, right? So what I'm saying is that if you are pairing 1 with some x which is less than equals to n, right, the others will have to have the same length, right? And unfortunately we won't have something inside of all of the points like here we had, right? If you do this, you can have all of these points completely, whatever configuration you choose, all of them will be completely inside these two, right? But here we can't have that. So if you pair 1 with x where x is less than or equals to n. You can't have that configuration. So in this case, since all of the segments should be of equal length, that means the segment length should be divisor of this. Why? Let me explain this with an example. So see, n is equals to 6, that's why we have 12 points. So how many divisors does 6 have? Like 4 divisors, 1, 2, 3 and 6, right? If I'm wrong, I mean, please correct me. So 1, 2, 3 and 6, right? So this is of length 1. So what you can do, you are creating a length 1 segment, and then you can repeat the same with 5 more times, right? The whole segment will be covered. This is when segment length is of length 1. Now other divisor is 2, so let's go with 2 length divisor, 2 length segments. So when we are going for 2 length segment, this will be paired with this. Now this is left unchecked, so this will be paired with this. Now all of the first 4 points are covered. Now the same configuration you can repeat 2 more times. So these 4 points will be covered again, and these 4 points will be covered again. That is, so you see what is happening. This I can repeat to this when n is equals to 1, it's taking 1 segment. How many do we have? We have like how many segment do we have? Just calculate it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. Okay, so these points are taken care of. Now these 2 points and these 2 points and these 2 points, so the whole segment length must be divisible by this. That's why that many x number of times we can actually repeat this configuration and the whole segment will be covered. Now when x is equals to 2, this is the configuration that that you will get, and after that you can repeat this whole configuration from here to here and then from here to here. Since you are adding this x number of time, that means the whole segment length is actually divisible by this length. Okay, now again divisor is 3, so go for 3 length and then again and then again. So this is your one configuration. Repeat it one more time here. So see, for segment length 1, 2 and 3 exists. Why it does not exist for 6? Even though I have told you that if n is the segment length should be divisor of n, right? 6 is divisor of 6. But thing is here, if you're taking one length segment, then 1 is being paired with 2, right? If you are taking 2 length segment, then 1 is being paired with 3, right? Basically, if you are going for x length segment, 1 is being paired with x plus 1. If you are going for 6 length segment, that is n length segment, then 1 will be paired with n minus 1, sorry. 1 will be paired with n minus, n plus 1. And if that is happened, this is observation 2, that will be case 2, not case 3, right? And that is why we will ignore nth divisor, the number itself, right? So 5 have 2 divisors, 1 and 5, so we will ignore 5. Okay, so 1 we will ignore, 1 divisor we will ignore, okay, from total number of divisors. So the final answer would be this from case 2, that is observation 2. dp of n will be dp of sum of dp of 0 through n minus 1 plus divisor sum of n, where we are ignoring n itself. Okay, here's the solution. So you see, this is the dp array, okay, and this is divisor sum. To calculate divisor sum, what we are doing, we are using sieve algorithm to calculate divisor sum, and here you see we are not including I itself. Okay, so this is using sieve and we are calculating divisor sum using sieve. After that we are running a loop from 1 to n, right? dp of I is sum of divisors plus prefix sum, right? For prefix sum we are using some variable. Okay, dp of 0 is equals to 1, it is initialized with 1, so prefix sum till 0, initially it is prefix sum till 0. Okay, and it will also be equal to 1 because dp of 0 we have defined to be 1, and there is a reason for it. I'm leaving this for you guys to figure out why we are doing this. There are many base cases where we define dp of 0 to be 1. Okay, so here this is for prefix sum, because dp of I is sum of prefix from 0 to n minus 1, I minus 1, right? So that is exactly this. dp of I is sum till I minus 1 and also divisor sum of I, and that is exactly what we are doing here. So the next time dp of this prefix sum should be dp of I. This basically, this also will be included in the prefix sum, and so it will be ready for the next I. Okay, and we have to take it modulo times for 9 plus 7, this is mod. Okay, after that you are simply printing dp of n. uh, there is a lot to take in for this problem. I took like 5-6 days to come up with all of these test cases and explanation and all of the thing that I'll be explaining. So it is possible that you won't be able to understand it in the first go. Try to take examples using and try to solve it using pen and paper. Okay, so you'll be able to understand it more thoroughly. So if you still have any doubt, you can ask in the comment section. So yeah, this was all for this lecture. Thank you guys for watching. Until the next video drops, keep coding. Thank you.